Hello everyone, myself Dr. N.CH.Ramgopal, working as Associate Professor in Mathematics in the Department of Humanities and Sciences, MLR Institute of Technology, Hyderabad. I welcome you all to today's session on residue at a pole using Laurent series. So today I am going to explain the procedure of finding the residue of a function f of z at a pole z equal to a using Laurent series expansion. So here in the last sessions we have discussed about poles, residues and the procedure to find the residues. And residue of a function at a pole can be obtained using two different methods. The first one is the standard formula to find residue, and the second is using the Laurent series expansion. So how to find the residue of a function f of z? So residue of f of z at a pole z equal to a using Laurent series expansion. First, expand the function f of z using Laurent series, or expand the function f of z as a Laurent series. Then the quotient of 1 by z minus a in that Laurent series expansion gives the residue of the function at the pole z equal to a. So residue is the quotient of 1 by z minus a in the Laurent series expansion of f of z. Let us solve some problems on the same topic. The first one, using Laurent series expansion, find the residue of this function. So solution, what is the given function? F of z is 1 by z into e power z minus 1. Now first we need to find the poles of this function. How to find the poles? To find the poles we need to equate the denominator to 0. What is the denominator here? Z into e power z minus 1. So equate it to 0. By equating the denominator to 0 we get z equal to 0 or e power z equal to 1. So z equal to 0, or if e power z is 1, what is the value of z? That is 2n pi I. This is using the expansion of e power I theta as cos theta plus I sin theta. E power 2n pi I is cos 2n pi plus I sin 2n pi. That gives 1 because sin n pi is 0. So here, and what is the value of n here? Where n belongs to z, the set of integers. That means 0, plus or minus 1, plus or minus 2 and so on. That implies z equal to 0 is a pole of order 2. And here it is required to find the residue of the function f of z at the pole z equal to 0. Now, let us consider the function f of z 1 by z into e power z minus 1. First we need to expand this as a Laurent series. So 1 by z into, we know the standard expansion of e power z. What is that? 1 plus z square by 2 factorial plus z cube by 3 factorial plus z power 4 by 4 factorial plus so on minus 1. So by simplifying this we get this 1 and minus 1 gets cancelled. Then again by taking 1 by z common, this is, so z in the denominator common, 1 plus z by 2 plus z square by 6 plus z cube by 24 plus so on. I will consider this as a single term. Now this is 1 by z square into, now let us take this denominator to numerator, so that we get 1 plus z by 2 plus z square by 6 plus z cube by 24 plus so on whole power minus 1. Now let us expand this using the standard notation. Standard expansions. 1 by z is equal to 1 by z square into 1. So we have 1 plus x power minus 1 is 1 minus x plus x square minus x cube plus so on. This is the standard known expansion. Here in place of x we have this z by 2 plus z square by 6. So 1 minus z by 2 plus z square by 6 plus z cube by 24 plus so on, plus z by 2 plus z square by 6 plus z cube by 24 plus so on, whole square plus minus and so on. Now by simplifying this we get 1 by z square 1 minus z by 2 plus z square by 6 plus z cube by 24 plus so on, and here square is there. So if you multiply the by squaring z square by 4 plus z power 4 by 36 plus so on, and now by multiplying this with 1 by z square, so we get 1 by z square minus, so here 1 by 2 into z plus 1 by 6 plus z by 24 plus so on, plus z square cancel 1 by 4 plus z square by 36 and so on, and nowhere we get this 1 by z term. Here we are calculating the residue of f at z equal to 0. So which is the quotient of 1 by z minus a, where a is 0 here. So quotient of 1 by z. Quotient of 1 by z we need to find. So that quotient of 1 by z is here. Nowhere you get 1 by z term. So here the quotient of 1 by z is equal to minus 1 by 2. Therefore, residue of f of z at the pole z equal to 0 is equal to minus 1 by 2. So, by expanding the given function as a Laurent series and finding the quotient of 1 by z minus a, we can find the residue at z equal to a. Similarly, let us consider another problem. Given f of z is e power z, z minus 5, and again at z equal to 0. So, first we need to simplify this e power z by z power 5, which is in the form of z minus 0 power 5. So, here z equal to 0 is a pole of order 5. Now, to find the residue at this pole, first we need to expand this function 1 by z power 5 into e power z, and we have the expansion of e power z 1 plus z square by 2 factorial plus z cube by 3 factorial and so on. So which is 1 by z power 5 1 plus z square by 2 plus z cube by 6 plus so on. Now by multiplying this 1 by z power 5 plus, so we need to expand this z power 4 by 24 plus z power 5 by 5 factorial. So 24 into 5 120 plus so on. So by simplifying this we get f of z as a Laurent series, multiply with 1 by z power 5. So 1 by z power 5 plus 1 by z power 4 plus 1 by 2 into 1 by z cube. Next this one 1 by 6 into 1 by z square, then 20 z power 4. So 1 by 24 into 1 by z plus so on. So this is the final Laurent series expansion of the given function. And here this is z power 5, z power 4, 3, 2, and here we have 1 by z term. So residue of f at z equal to 0 is the quotient of 1 by z minus 0. So quotient of 1 by z. What is the quotient of 1 by z here? 1 by 24. So the residue of the pole at z equal to 0 is 1 by 24. Similarly, consider the function f of z 1 by z square into sin hz. So here the residue at the pole, so z equal to 0 is a pole of order 2. Now by using the expansion of sin hz, now we have sin z expansion. In trigonometric functions, sine function, the sign changes alternately. So z minus z cube by 3 factorial plus z power 5 by 5 factorial minus z power 7 by 7 factorial and so on. But in sin hz, the pattern is the same, but all the terms are positive. So z plus z cube by 3 factorial plus z power 5 by 5 factorial plus z power 7 by 7 factorial and so on. So this is the expansion of sin hz. Z plus z cube by 3 factorial, z power 5 by 5 factorial, z power 7 by 7 factorial and so on. So this is equal to 1 by z square into, here take z common, 1 plus z square by 6 plus z power 4 by, so 5 factorial is 120 plus so on. So 1 by z cube into, this goes to the numerator, z square by 6 plus z power 4 by 120 and so on, power minus 1. Here we can take this as a single term. So that means the Laurent series expansion of the function f of z is 1 by z cube into, now 1 minus z square by 6, z power 4 by 120, then plus the whole square of this function. So here also we have minus and so on, plus z square by 6 minus z power 4 plus z power 4 by 120 minus, so plus so on, whole square and so on. That's equal to, by multiplying with 1 by z cube, we get minus 1 by 6z minus 1 by 120. So here z comes in the numerator and so on. So the residue of f at z equal to 0 is the quotient of 1 by z. Now what is the quotient of 1 by z here? Minus 1 by 6. So you, by expanding the given function as a Laurent series and finding the quotient of 1 by z minus a, we can find the residue of the given function at the given pole z equal to a. So today we have discussed the procedure of finding residue of a function at a pole z equal to a using Laurent series expansion. And how to find the residue? So the residue of f of z at z equal to a is the quotient of 1 by z minus a in the Laurent series expansion of f of z. So in the next session also I am going to continue the same topic, so as a part 2, and we find the residue of the function f of z using Laurent series expansion. This is for today's session. Thank you very much.